of this term. And I'm gonna start with land acknowledgements. I have observed Orange Shirt Day a couple of weeks ago, and I was thinking, yeah, I am teaching in this university standing on the traditional ancestral and unceded territory of the Musqueam people, and made me realize that oftentimes, or in many cases, we have seen from the history of the residential schools, an educational institution can serve as the device for oppression and discrimination. So that made me think we should discuss and uncover what has been done to those who are oppressed, and then we have to advance what we are doing under the name of the educational agenda. So that's what I want to share as the land acknowledgement. Yeah, and a pre-announcement for the upcoming talk by Dr. Cindy Bourne, who is the head of the CTLT at the UBC Okanagan, and she's gonna talk about her exciting project on how she enabled women's education in rural Ghana, Africa. It's gonna be a very interesting talk. If you're interested in women's experience, supporting their education and enabling them through design solutions in the rural context. Today, we will have Charles Perin. Professor Charles Perin is an assistant professor of computer science at the University of Victoria. He has been the most visible in the domain of visualization. He has published many impactful papers to InfoVis, IEEEVis, and some of the HCI conferences like SIGCHI. And before joining the University of Victoria in 2018, he was a lecturer, equivalent or synonymous to the assistant professor at North America at the City University of London. Before that, he worked with Sheila Carpendale, a frequent company with TFP, as a postdoc at the University of Calgary. And before that, he did his PhD at INRIA, Paris. Now, Charles is co-leading an interesting initiative at University of Victoria Computer Science called Victoria Interactive Experiences with Information, VIXI. I think it's an interdisciplinary research group that is co-led by professors Charles Perin, Soumya Somanath, and Miguel Nacentas. If you're interested in what's going on in HCI and visualization front at University of Victoria, you may want to have discussion with Charles about that and potential for networking and collaboration. Today, I believe Charles will talk about flexible visualization, very interesting topic. I have been inspired by many works in natural user interfaces or reality-based interactions. So I think that has some conceptual relevance to those line of studies. So looking forward to that, Charles, taking my mic over to you. Go ahead.
Thanks a lot for the long introduction. So let me make sure I got these slides right.
Just want to make sure if we are sharing the screen.
We are screen sharing, yes. Okay. All right. Thanks for having me. That's, I think, the first talk also I give in 24 months. Besides teaching in the classrooms that we're starting doing again. So yeah, I'm really excited to be here and finally be able to visit in person, have some discussions with real faces. I want to talk about what I call flexible data visualization interfaces today, which is kind of a take on the kind of research I've been doing in the past 7 or so years, a specific perspective that I've been using to look at some of my previous work and where we can go from there. I'll start with an anecdote. So it was a few months ago, I was going through the IBM Cognos webpage, and I saw this. So smarter business intelligence, let AI help you uncover the patterns hidden in your data. It doesn't just show you a bar chart, it interprets the data for you and presents actionable insights in plain language. So that looks cool. Computers are going to save us all, but it's also basically saying that showing the data maybe doesn't really matter in the end, but you don't really need to look at the chart because the computer will write for you the sentence, right, that you can use to communicate. And I'm pretty sure that I'm not the only one in this room or in your other rooms virtually to be a bit scared by this kind of language. But also this fear is really not new. It's been around since the early ages of the data visualization. So I have a small nugget for you that's from a movie from the French National Archive that we digitized while I was doing my PhD in Paris in 2013, I think.
Oui, je sais ce que tu vas dire. Qu'est-ce que je veux dire? Tu vas parler de l'informatique. Les cartes perforées, les programmes, les calculatrices, des chiffres, des chiffres. Oh, et puis les machines, on met des chiffres à l'entrée, et à la sortie encore des chiffres, on ne sait toujours pas ce que ça veut dire. Et puis, l'accès à la machine, ça vaut des sous. Moi, les calculatrices, ça me fait penser à la pitié dans la Grèce antique.
Esprit de l'ordinateur, es-tu là?
Oui, je suis là.
Que fais-tu là?
Je me fais adorer des foules menées par leurs technocrates.
Non, 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 je ne veux pas te parler de l'ordinateur, au contraire. Je veux te parler d'une méthode que tu peux utiliser toi-même en vérifiant tout, où on voit toutes les choses se mettre en place. Et je crois que je t'avais déjà parlé d'une méthode comme ça. La graphie.
So, like with this movie from the 70s, besides the fact that they could drink red wine for an educational movie, it reminds us that people have tried to make sense of data, of numbers for decades. So we didn't wait for this big data revolution to ask these kind of questions. Anyone wants to guess who made this movie? Who is the guy on the right drinking wine? No idea? Okay. That's our friend Jacques Bertin. So he's a French cartographer. He wrote one of the most influential visualization books that you might know of. It's called The Semiology of Graphics. I actually had a great talk with Tamara yesterday over dinner about some of the things that he wrote in his book and how he might be wrong sometimes. So Bertin wrote another much less famous book that was translated as Graphics and Graphic Information Processing, in which he described a method for analyzing data. And the key to this method was interaction. He didn't call that like that at the time. He called that internal mobility. And he believed that interaction is what makes visualization that powerful. So he calls this method la graphique. And so here is another very short excerpt from the movie that illustrates actually what he means by this internal mobility. Here you have plastic cubes that create a physical version of a table of binary values. That describe whether some towns have some given attributes, doesn't really matter, but a white cube means no, and a black cube means yes, I have this attribute. And so internal mobility of the image here is achieved by inserting rods, either horizontally or vertically in these cubes to manipulate directly the rows or the columns of the table. And the idea is that through iterative manipulation, you do that for quite some time, then patterns start to emerge. And in his lab in the 70s, they created such devices to help a lot of people make data-driven decisions, like shop owners, researchers, clients, hotel owners, etc. And with colleagues, we built a replica of the device and we observed people interact with it during an exhibit on Bertin in Paris. I think when you are there. And you can notice how people interact with the visualization. They move around it, they point at things, they collaborate, they manipulate directly the wooden pieces that represent the data. And so it always makes me think that visualization tools that exist out there, they're really limited in terms of how they allow people to interact with them. Very far from what people will do around this kind of physical device. That allows you to grab data points in your hands, to move around freely, to work in groups, etc. Even to use your whole body to explore the data. And so the one theme of my research on interaction with visualization in general that I want to talk about today is that we need more flexible data visualization interfaces. So why is that? Well, I'll attempt to convince you that first, to perceive data and information with visualizations, it requires interaction, but that also our standard ways of interacting with visualizations are not as easy or discoverable or intuitive as we may think. And actually, there are many more ways that people might interact with visualizations than the standard ways if they are given the opportunity. Because people actually interact in many diverse ways. All right, so first of all, perception requires interaction. Where does it come from? We've known for a long time that to perceive something, we need to interact with it. So if we manipulate physical objects, like we weigh them, we touch them, etc., it gives us some feedback that we perceive through our senses, and we then interpret what we just perceived. We learn, and we can draw conclusions, etc. And in data visualization, this can be as simple as just getting closer to something, right? A physical zooming to read more details, or just touching a 3D printed bar chart to get a sense of the height of that. Or with this kind of research, it's about manipulating the data directly, creating some kind of freeform layout without constraints. A bit like what they were doing with the physical matrix that I showed earlier. So perception of information requires action, and when it comes to visualization, it requires what we call interaction. But what exactly do we mean by interaction? And I think it's important to have a common ground here. There has actually been some work in the HCI community a few years ago about trying to do the same thing, trying to define what we mean by interaction in HCI. And so with my colleague Evantia Dimara, we tried to answer this question for visualization, really based on that observation that as a community, we all have our own idea of what interaction means, and what it can be, and what it should be. So I won't go into details, but basically we collected important interaction papers, specifically in visualization research. Actually, thanks to the generosity of our community, like I think Ben and Tamara contributed to that, actually. Then we analyzed these papers, we tagged interaction themes to extract what we as a community mean by interaction. And then we compared that to the view from the field of HCI using these recent surveys that are also attempting to do the same thing. So to arrive at a definition that is really specific to visualization. So I read it first. That interaction for visualization is the interplay between a person and a data interface that involves the data-related intent, at least one action from the person, and an interface reaction that's perceived as such. It's a mouthful, but in other words, but simply, it requires a kind of communication, of dialogue, between an individual, an interface that represents data, like a visualization or a physicalization, any other ways of representing data. Then we need the person to have an intent that's related to the data, like I want to remove a data point, for example. And to do something with the interface in relation to that intent. Like, for example, I select the data point and I press the delete key. Afterward, the data interface must respond something, for example, by removing the data point or making some sound, so that the person perceives this response, for example, through their visual system, auditory system, and the key is that they understand that the response is as a response to the action. All right, I'll come back to this definition later, but at least now you have an idea of what I mean when I use the word interaction. So we've known for quite some time that perception with visualizations requires interaction. And the thing is, we've been interacting with visualizations for quite some time as well. But I also argue that the interactions that we implement in our visualization interfaces are both fairly standard and rigid. So I have another short video, a bit less old, like from the early 90s, that demonstrates dynamic queries from a famous person that you might have heard of.
I want to be from point A, and now it's set at 30 miles, and I'm going to bring it down, and you can control rapidly, incrementally.
So basically, by changing a slider, we can filter the data points that are based on their distance to a given point. It's a really powerful interaction. This has become a fairly standard way of interacting with visualizations, although actually often its implementation is not on par with this one. But yeah, it's this kind of interaction has become really standard, and tools like Tableau and so on, they are still based on this model. They rely on menus and icons and widgets like some sliders and checkboxes to filter the data, to interact with what you see, and drag and drop operations, etc. Basically what we call WIMP interfaces. They work great. They're used by millions of people. And the thing is, we think to assume that these interactions are so common and standard that people will end up easily using these tools. So this reminds me a bit of this great paper that influenced my research a lot from 1999, in which Broaden took a stand against the at the time guideline of maximizing interface consistency. And if consistency can help people transfer knowledge and learn systems, it also tends to lead to rigidity. So interaction consistency seems to live on this assumption that everybody interacts with interfaces in the same way. Actually, not only are consistent interfaces not that easy to discover, people being people, they also have individual preferences and strategies when they interact with visualizations. And so that's what we looked at in this next project here, where we used a website that consists of 4 visualizations. Each chart shows aspects of energy-related data that we had built in collaboration with the Canada Energy Regulator in Calgary. It's accessible online somewhere on the government website. And in this kind of visualization, the person can interact by manipulating buttons, selecting different regions in Canada, reorder them, use other standard buttons, right? And so we had people come to the lab, and we just asked them to explore the data on the 4 different views without specific tasks, to try to have a somewhat realistic scenario, but where we could also collect eye tracking data and interaction logs and things like that. Yes, that was before the pandemic, I guess. And we segmented each interface using different areas of interest, as we often do with eye tracking data, based on whether they contain controlled widget in orange, the charts that are in purple in the middle, or the numbers that are in blue. And then we could create interaction sequences based on where the participant was looking, what they were interacting with, which area, and what they were saying as well. So combining all of these data sources together. And we created many of these timelines, and then we did qualitative analysis of them and identified 7 stereotypical exploration strategies that people were using. But I'll just mention 3 of the strategies that are concerned with how participants discovered the available interactions. So the first one is that all participants at a point, they tried what called opportunistic interactions, where basically they tried their luck a bit randomly to learn the interface through trial and error. So in short, the feeling that none of the participants was confident enough that they didn't need to tinker at first with the interface to make sense of it. The second one that was also used by everyone is a variant where they used the structure of the interface, the widget, to explore the different options. So, for example, they would try all energy sources at the top. in sequence, right? So it's less random, and it shows that people are trying to make sense of the controls, what they meant. And the third one is what we call permutation interactions, where a quarter of the participants had this even more methodic exploration, and they tried out the widgets in a hierarchical way. So here, for example, we have the participant try one source at the top and then changing all the different scenarios at the bottom to kind of have a hierarchical exploration of the menus. They felt that they had to explore all possible combinations of options. Overall, what we found is that the participants, they did indeed interact with the interface, even with an interface that relies on very standard widgets with buttons and icons. Most people had to make guesses around about which interactions are available. And why is that? Is because perhaps these generic interaction widgets are suited to some very specific ways of interacting. If you think about it, clicking on buttons and menus is probably the least natural way that people would interact with the visualization if they could choose, right? Something that we have imposed on ourselves. And that's something we looked at with what you call the concept of active reading of visualizations, where we observed people interact freely with the visualization. Okay, before I go there, I need to explain what active reading means. So active reading was introduced in this book called How to Read a Book by Adler and Van Doren. And the idea is quite simple. So with active reading of text, you have a primary task that is to deeply engage with the text. And this primary task is supported by a number of secondary tasks that are techniques that you can learn, that you can apply. For example, highlighting, or taking notes, or viewing the document in a different way. So these are active reading techniques that you apply. These secondary tasks basically are interactions that you can perform with text, and then help us move from simply taking in the information to actually elevating our understanding of it. So that's for active reading of text. And of course, the question is there a parallel that we can make with visualization? Do we actively read visualizations the same way that we actively read text? So we asked some visualization novices to solve some simple problems related to a paper-based node-link visualization, this one, a small social network dataset with some different types of relationships. And we incorporated some basic interactions, like link filtering that was supported by printing different types of links on separate sheet of paper that you could actually also stack on top of each other. And we printed each type of link on a separate sheet. Provided also tools like markers, etc., and eraser. And how participants behave to solve this problem was quite fascinating. So you can notice in the videos how like the amount of activity that's happening. People are not just staring at the visualization. They are using their hands, they are moving the visualization around, they are actually writing on the visualization sometimes. They use many views, many layers, etc. Count on their fingers and so on. And so following this observation, we analyzed these videos and we identified a spectrum of how physically engaged the participants were when they were analyzing this visualization. We found two main categories of actions, the ones where you don't change the visualization anyway, and the ones where you actually do change the visualization. So here are a few examples that show a bit the extent of this physical engagement spectrum. You have looking actions where they happen anytime someone just change their point of view by looking elsewhere. Following actions, when you reference the visualization but without making contact, like tracing in the air, or if you tap the pen as if you are counting. And contact actions, where you start making contact with the visualization, by pointing or tracing the visualization with your hand. The second category is where participants made some sort of physical change to the visualization. So we had positioning actions, where that involves moving some sheets, changing the point of view, holding the sheets in various orientations. Some made marks directly on the visualization, like annotations, highlights. They also erased some of those marks. And they also created new marks on other sheets of paper, creating their whole new visual encodings, for example. So what did we do with that? Well, we could then map these actions to the goals that they had when performing these actions. What were their intent behind them? And there are 5 goals, which are to recognize information, to track information, for example, when you look and follow, to reorganize the information when you move the sheet, let's say, to decode and encode information also when you make new marks, and finally to analyze information using, for example, annotations or calculations. So we have these goals, and to achieve these goals, we have these actions, sorry. So it's clear that we need to interact, to actively engage with the visualization in various ways, not just look at it. Right? And so the key here is also the various ways. People are doing many different things to achieve the same goal. So various way is kind of the opposite to a single way that would be decided by me, a visualization designer or UI designer. Or that would be based on a guess of what people, what kind of tasks people would want to perform. But instead, various and complex, diverse ways. The thing is, this experiment was using paper, and we were clearly probing their reaction by giving them some material. So the question is that also true for more standard desktop-based digital visualization? That actually supports so little in terms of physical engagement compared to a physical space where you can move around. So yes, to a certain extent. In this next work, we looked at a more flexible paradigm of interaction with visualizations, which is called the direct manipulation of graphical encodings, where basically you manipulate the visual marks that represent data directly. So we wanted to know how people would interact with visualization to accomplish visualization tasks. So for that, and without relying on standard interactive controls, so we asked participants to perform a series of these 15 relatively standard visualization operations, and to demonstrate how they would perform each of these tasks solely by directly manipulating the visual marks, the graphical marks. A bit like you would do in Illustrator, right? We asked them to do it for bar charts, for histograms, and for scatter plots as well. So here's an example here. If we ask the participant to sort the bar chart, they might express their intention of doing so by reorganizing just a couple of bars, the smallest one and the tallest one, to extremities of the chart. And then they assume that the computer will interpret their intent correctly and help them sort the bar chart. So we had a lot of video to, again, analyze that we open coded for all these operations. And from that, we identified 48 different strategies that people use to achieve these different operations. Interestingly, we thought originally that people would come up with many, many different strategies to perform each of the 15 operations, because there was no constraint, right? Besides use this kind of toy interface, but you could do whatever you want to try to express your intent. But when you look at the results table, where you see all the 15 operations in row, and then the 48 strategies that are identified in column, and the number of actually the shape of that indicate how many participants use that strategy for that operation. It's a very, very sparse table, right? For some operations, there was actually a high level of agreement among participants. So for example, to sort a bar chart, the one I showed earlier, participants employed only 5 different strategies, and only 2 of these were employed by more than one participant. So among these 5 strategies, there was the one I already talked about. You reorder a few bars. You think the system will understand that you want to sort it. And 3 participants only moved the tallest and the shortest bar to opposite extremities of the chart. So that's an example where most participants did the same thing, but in contrast, we had some operations that led to much more diverse strategies. So for example, we found 8 different strategies to switch from a scatter plot to a bar chart, and there was no clear winner, right? It was quite spread. And there were also strategies that were used. So the same strategy was used to perform different operations. As you can see here, the same strategy is used for 4 different operations. So for example, to signify that they wanted to group several bars into one bar, merge the bins of a histogram. Some participants decided that it would be a good idea to color these bars using the same color. Color both red, it means I want to merge them. But then other participants employed the exact same strategy to color these 2 bars to signify that they wanted to recolor all the bars. The same strategy for 2 very different intents. Overall, it looks like there are some strategies that many people will employ to perform a given operation. And these are likely good candidates when it comes to deciding which strategy your system should support. But there are also some operations for which there is clearly no consensus, and some strategies that are conflicting because they are used to invoke different operations. And that's again, of course, because people are different. And actually from these 48 strategies that they use, they selected these 3 higher level strategies that capture people's different interaction styles that we call exemplification, declaration, and instrumentation. I'll give you examples of each. Some participants, they like to use exemplification. So basically, they directly manipulate a small number of visual marks to illustrate by example what they are trying to produce, to achieve. So to sort a bar chart, they would only manipulate a few bars, right? Or if they want to recolor all data points, change the color of all data points, they would just change the color of a couple of them and then think that the system will understand. So that's exemplification. Some use the concept of declaration, which is a bit odd, I find. I mean, a bit difficult to wrap your mind around. But with this interaction style, basically what they did is they manipulated a graphical encoding that is different from the primary graphical encoding that is used in the operations they are trying to achieve. So I'll give you an example. This image here, in the center, it shows a bar chart, and they want to order the bar chart. So if you want to order a bar chart, the primary encoding is the height of the bars, right? But instead of using the height of the bars to express their intent in reordering the bar chart, they created a new encoding, a secondary encoding that is color here, where they created kind of a temporary custom color scale to indicate that in their mind, it goes from yellow to orange to red. So it means they want to sort the bar chart in that order. Okay. Where was I? Yes, the third of this higher level strategy is instrumentation. And so with this style, what participants did is that they turned a visual mark from the visualization into an instrument, into their own tool, to perform some new operations. So this resulted in some very unexpected and interesting strategies. So for example, the 2 strategies that I'm showing here on the right, they were used to recolor a subset of data points in a scatter plot. And so the first one at the top that we call recolor and deep, with with that, what they did is that they first selected a data point, changed its color, and then they used it as a bucket of paint. They were dragging other data points to it so that they would take the same color and then they would go back to their position. And the one named recolor and paint is a bit similar. They also first change the color of a data point, but then they use it as a brush to brush over other data points to change their color as well. So basically, the data points become these interactive tools. All right, so this study shows not only that there are some more direct ways of interacting with the data than widgets and menus, but it also shows that people can sometimes intuitively use some original means of expressing their intentions. And above all, that they interact in really diverse ways again. They use diverse strategies and they have diverse interaction styles. So understanding and leveraging this diversity of interactions, if we were to create more flexible interfaces, I think would clearly help in improving the discoverability of these interfaces, of interaction in visualization, and make visualization more accessible as well. I've talked a lot about flexibility, bold orange here, so maybe it's time that I explain what I mean by that. And actually, the concept of flexibility is one, sorry, that's a difficult word, one operationalization of this definition of interactions that I presented earlier. So by analyzing interfaces from the length of our definition, we could classify visualization actions and propose this definition of flexibility, which is the number of distinct allowable actions of a person on the interface, as well as the number of interaction means with which the person can perform each action. So again, in short, it captures the number of things you can do with the data interface, the different ways you have of doing each of these things. So the cool thing with this concept is that it allows us to describe, compare, and evaluate very different systems from that perspective. I have a quick toy example. At the home finder on the left, that is like dynamic queries that I showed at the beginning, and constructive visualization, which consists of mapping some individual data points to individual tokens. And we can analyze these two seemingly very different data interfaces through the lens of flexibility. If we look at the actions that relate to data processing in the first row here, you could say that when it comes to making a data query, the home finder supports several ways of querying the data, like using sliders, dragging and dropping icons. But the physical tokens, they don't support any interactive query at all. Now, if we look at input actions, the home finder interface doesn't support adding new data points, while it's easy to just add a new token. And same is true for correcting or deleting data points or adding metadata as well to a data point. So the idea is not to be exhaustive here. It's really a toy example, but the point is that some actions are sometimes supported, sometimes not. And there are sometimes also several ways of achieving the same action. And both these aspects contribute to flexibility. So if flexibility is needed, and we can evaluate the flexibility of data visualization interfaces, how can we actually act on that? Because the truth is, designing interfaces that are more flexible is really difficult. It's very, very hard. So I have an example for you. It's a hybrid digital physical interface, where I think that's a very interesting space to look at this kind of interfaces. Because if you remember about the spectrum of physical engagement I talked about with active reading, if we go beyond desktop interfaces, we can allow people to use their full body to interact with data the same way we interact with objects in our lives. So this work builds on recent work on what we call physicalizations, physical representations of data, that have been shown that they can help novices learn about visualization. They can support data exploration. They can be good for storytelling. And this work beyond physicalization also draws from this observation that there's been a lot of research on designing digital screen-based visualizations, like the one that you see here, that copy the physical world, like the wind kinetica here. It relies on physical simulation. But could we instead perform these physical operations on physical objects using our whole body and senses as opposed to using a mouse or fingertips, right? And on the other hand, can we bring the kind of automation that we see here also to physicalizations that tend to be very static? But I did some work in that space with shape-changing displays, for example, create 3D bar charts with these zoids that are self-propelled micro-robots that can move around. And zoids are what I'm going to use in this example to talk about composite data physicalization. So if we look at physicalizations in general, we can talk about them in terms of how manipulable they are. That's the extent to which the elements that represent data can be manually rearranged, but also the level of actuation, which is the extent to which the elements can rearrange themselves. And then we can place existing physicalizations in that space, like the 3D bar charts that are static and not designed to be manipulated, these tokens that are more manipulable, but also static, the matrix I showed at the beginning. And so far, most of the physicalizations have actually been static, and dynamic ones seldom support manipulability. So we wanted to explore the top right corner, of course, of that space, and that's why we have this idea of composite physicalizations. And so there are these physicalizations that represent data using multiple elements and whose topology can be reconfigured or reconfigure itself. I have a scenario to illustrate a bit the concept. Here, we have a committee of 4 faculty members. They meet to examine some grad student applications. And these zoids here, these robots, they embody students with their application details. So president of the committee take their tablet to load the data set that contains the student, and then they just move toward the center of the table. And the committee can then start exploring the applications by examining the grade in science, by assigning a science grade to one of these zoids. And what it does is that it creates a blue magnet, and then the students start converging towards that magnet based on their grade in science. You create a second magnet, like the math grade, for example, and you can see how students perform in both math and science. So these are examples really of automation and actuation. But when students move to their new position, if you realize that a group of students are, has clustered in between both magnets, and you agree that these are excellent, you can, for example, take a piece of paper, draw an array on it, and put it underneath, right? Basically creating a physical annotation. And if you realize that one of the students has a very low score for their cover letter, you want to get to discard the student, so you simply put them in a reject container, right? So these kind of interactions, they illustrate control, manipulability. If they want to compare the 4 students they selected, then you can place a cover letter magnet on one axis of a scatter plot frame, a portfolio magnet on the other, and then you put the students in the frame, and they arrange themselves according to these dimensions. And you start to see that one of the students turns out there. Okay, skip this one. And that's another example of a scatter plot where you use, latitude and longitude, and this is an overlay of the map. So what I find great with these kind of these physicalizations is that combining manipulation and automation in the physical world, it alleviates some of the problems of static physicalizations, and also it allows for a much larger spectrum of physical engagement to interact with the data. Like making annotations, if you want to remove data points, you can just take them in your hands. If you want to filter data points, you can just push them around, etc. And some of these interactions are very difficult to implement, actually, on a digital system. And at the same time, yes, we don't have to manipulate each data point individually and painfully like they were doing with this matrix in the 70s. Okay, I'm nearing the end of the talk. So I focused on leveraging physical visualizations to design some more flexible data visualization interfaces, but there are many more ways to do so. And more visualization researchers are looking in these other directions. I'll just throw a bunch of words. They include, for example, the use of virtual, augmented reality, cross-device visualization, multi-sensory perceptualization, multimodal interaction, etc. And also AI, natural language input, etc. So all of that basically can get, so that we can get better automation in response to our interactions. I just hope that we leverage these technologies to make our interfaces more flexible and more accessible, right? So that we can support a more diverse range of interaction styles, not just constrained to one, and that we don't just reproduce what we've been doing for many years in our interaction comfort zone, right? It will require a lot of work because, as I said earlier, designing these kind of interfaces is really hard. I think it requires conducting many studies to understand really the diversity of these interactions. In the visualization community, we publish hundreds of stories to understand how people perceive information. But we really overlook these interaction studies, try to understand how people interact actually. But they are probably at least as important. And also, yeah, more specifically, I think that these interactions are perhaps even more sensitive to people's characteristics and cultures and gender and so on, who might have more different interaction styles, preferences, and perception differences. And also, there are, of course, very hard technical challenges. We try to build a system that would support just two different interaction paradigms simultaneously, and that would be cross-compatible. And it's really, really, really difficult. There's a paper on arXiv about it, but just shows that we failed, I think. So that's the end of my talk. I just want to finish by mentioning two things. There is a VIS conference happening a week from now, 10 days from now. So I'm very involved in the arts program. That's really cool, the intersection of visualization and arts. And also in this AltVis workshop that I encourage you to check out. It's kind of the AltCai, but we're bringing to Viz. We have a lot of very provocative work around visualization there. And finally, just echo what Tangut said at the beginning. We have created this lab now a year and a half ago in Victoria. We have quite a few students already, together with Sonia and Miguel. And so we do a lot of work around visualization and HCI, also tangibles, creative computing, digital fabrication, modeling. Miguel does a bit of machine learning as well. Yeah, we're very much looking forward to expanding our network of collaborators and working on many kinds of projects. Thank you.
Thank you, Charles. That was fantastic. A couple of announcements before Q&A.
Sure.
Due to time, Charles, do want to reach out to the researchers in UBC and Vancouver. So